All right, let's continue in types of reactions in chapter 4 and look at acids and bases. So to do this, we need to start out with some definitions. We're going to look at Arrhenius acids. We're going to have two definitions of acids and bases here, but we're going to start out with the oldest, which is Arrhenius. An Arrhenius acid produces an H plus in water. So if we look at something like HCl, it's going to break into water and produce an H plus and a Cl minus. Acids have a sour taste. They turn blue litmus paper red, the red for the R in the acid, if you want to take a look at that. And some metals will react with them and they corrode. If we've got a pH that is going to be below 7, so if we have a pH that's less than 7, we're going to have a solution that is acidic. So, Arrhenius bases. Arrhenius bases produce hydroxide in water. Now, we don't tend to eat them because they tend to taste very slippery, or feel slippery or soapy, and they taste very bitter. They turn red litmus paper blue, and we can get some interesting reactions when we react acids and bases. But here, we need to remember that they produce OH minus in water. Now, these are quite different. So acids ionize in water. They don't dissociate to form H plus ions. So if we had HCl or HNO3, and these are both strong acids, by the way, where strong means strong electrolyte, we put them in water, and they're going to break into their pieces. But when we say this, because they're not actually ionic, we say they're going to ionize rather than dissociate. Bases, on the other hand, tend to be group 1 or group 2 hydroxides. These are going to follow the solubility rules, and if we take something like sodium hydroxide and we put it into water, it is a strong electrolyte because all group 1 compounds are soluble, and it's going to break into sodium and hydroxide. When we take and react these, and if we wanted to take and react NaOH with our HCl. This is a double displacement or double replacement reaction where we're going to take the hydroxide and swap it with the chloride. We're going to make NaCl. NaCl is an ionic compound, which we also called a salt. And the easiest way to look at H plus with OH minus is to realize that if we take H plus and we react it with OH minus, we're going to make HOH. And HOH is simply the same as H2O. So if we take an acid and a base in the simplest type of reaction, which is an acid-base neutralization reaction, we're going to make a salt or an ionic compound plus water. How do we spot acids? Acids frequently have hydrogens in the beginning of them. Organic acids we write a little differently, but right now we're going to look for a hydrogen in front. And at the end, we're going to use the word acid. If we take and we need to separate the difference or look at the difference between HCl as a gas and HCl as an acid, HCl as an acid would be aqueous. Acids are in water. These guys as a molecule would be gases, and we would not name them the same. So the best way to do this is to realize they have the H plus in the front. They're in water, and we name them whatever this is with an acid. Remember, adic itis hydrorutic. So, acids ionize in water. Now, unfortunately, it's not quite as simple as Arrhenius suggested, where if we had the HCl and we put it in water, we made an H plus plus a Cl minus. The problem is H plus, which is a hydrogen without its electron, is actually just a proton. And a proton is a subatomic particle, and a proton is not stable. Protons are going to react with something, and in this case, the protons stick to water to make a new ion, and it's going to be hydronium. So by far the best way to write this is to take a look at our strong acids. By the ones, the strong acids react completely, or at least almost completely. HCl is one of those. We take HCl, we put it in water, we're going to make H3O plus plus Cl minus. The key being that this H plus here is going to stick to a water and make H3O plus. Now, those are our strong acids. They break apart entirely. Weak acids only ionize slightly. HF is a weak acid, and if we put it in water, instead of having one arrow, which means, by the way, 100%, we have two arrows, which means it goes in both directions, so it's not 100%. It will still make hydronium and fluoride, but most of the HF does not, in fact, react. Most of it stays as HF, aqueous. It's still dissolved, it's just not ionized. As a graphic, how would you do this? Well, if we had HCl and we put it in water, this chloride here would stick to, or would be surrounded by the water as just the ions are in a solution, and this H plus that's off the chloride is going to stick to the water, and we're going to make H3O plus transferring a proton. By the way, we call this a Bronsted acid. A Bronsted acid rather than an Arrhenius acid. A Bronsted acid is a proton donor. So if we look at HCl, HCl donates its proton to water. We're going to deal with that definition a lot more in Chem 112. These are some commonly occurring acids, and we use them for all sorts of things. Hypochlorous acid contains the ClO, which is in bleach. Carbonic acid is what's in our sodas. Hydrofluoric acid is nasty, and we use it for etching glass. Acetic is the acid that's in vinegar. Chloric acid actually is used in explosives. Phosphoric is used as a fertilizer. And the rest of these we see around for all sorts of interesting things. The ones up here that have lots of oxygens can be used as explosives, and they're pretty cool. Bases are almost exclusively a metal with a hydroxide. That's it. Metal with hydroxide is going to be bases. These guys are insoluble. We know this from the solubility rules, and these guys are soluble. And again, we know this because all group 1 compounds are soluble, and barium is one of the soluble exceptions on the hydroxides in the solubility rules. These are some common bases. We see them around. Milk of magnesia is an interesting one. We actually use this as an antacid, as we do sodium bicarbonate. Sodium bicarbonate will also produce carbon dioxide when we cook, and we use that to produce bubbles in our food, like our cakes, and make them light and fluffy. So what do you need to know? You need to memorize strong acids and the strong bases. The strong acids are nitric, hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, and sulfuric. Commit those to memory. Those are your strong acids. Our strong bases come completely off the solubility rules, and they are NaOH and KOH. We also have some of the other ones from group 1. They're just not as common. The other ones that commonly occur are the group 2 exceptions to the fact that the hydroxides are insoluble, and those are calcium, strontium, and barium hydroxides are also soluble, and these are our strong bases. Remember, strong base means strong electrolyte, which is going to mean 100%, in this case, dissociated, and in this case, ionized. Okay, in water, strong acids and strong bases. So again, what happens if we take and do HCl plus NaOH? This is an acid-base neutralization reaction. And what happens when we take and we put these together is we're going to have our HCl, we're going to have our NaOH. Note our Na and our OH are dissociated, and we're going to take and put this together, and we're going to leave our sodium chloride sitting there with our water. If we think about this, we can write an interesting reaction because we can write a total ionic. We recognize that HCl is strong. It is going to break into H plus Cl minus. It's going to react with sodium and hydroxide to make sodium and chloride plus H2O. Now note, we can stick this H plus onto a water. We're really not going to Chem 111. We just kind of need to recognize that that's actually a proton and it doesn't exist in water. But for right now, let's look at our spectators. Our spectators are sodium and chloride. They were up here sitting by themselves, not part of the reaction. Here, they're sitting by themselves, not part of the reaction. And the only thing that has changed is the fact that H plus has reacted with OH minus to make H2O. This is the net ionic reaction for an acid-base neutralization. Now, we do need to consider strong with weak. So let's instead consider HF if it reacts with potassium hydroxide. So HF is a weak acid. If we react with potassium hydroxide, our products aren't going to change. We're still going to make water and the salt. Our salt is going to be KF aqueous plus H2O as a liquid. All right, those are our products. But we need to consider what HF means. Because this is not strong, therefore this is weak, and this is strong, and this is soluble. And remember here that strong, in terms of an ionic compound, means it's going to be broken into its pieces. But because HF is weak, it's not broken into our pieces. Our total ionic equation would be HF aqueous plus K plus OH minus goes into K plus F minus plus H2O as a liquid. Now, because all of the HF over here isn't broken apart, our net ionic is going to change. The only thing that is a spectator that is unchanged on both sides is the potassium. So if we rewrote this now and we did our net ionic for this is HF aqueous plus OH minus aqueous goes into F minus aqueous plus H2O as a liquid. And the fact that that's a weak acid means it doesn't dissociate 100%. It's going to stay as HF. All right, back to acid-base neutralization reactions. Acid-base neutralization reactions are going to be a strong acid with a strong base, goes into a nice inert salt, and inert means nice and soluble, and some water, where our net ionic equation is always going to be H plus OH minus goes into H2O, and this works as long as the salt that you make is soluble in water. So let's do a few. All right, we understand HCl plus NaOH going into NaCl in water. But if instead we take nitric and calcium hydroxide, we know that, again, this is a double displacement, and we're going to put the nitrate with the calcium and the hydroxide over here. We're going to make waters. Because our net ionic is always going to be H plus OH minus goes into H2O, we can realize that because we have two hydroxides in the calcium hydroxide, that's going to be a 2, meaning we have to have two H pluses, and we're going to make two H2Os. So we can put a 2H2O over here. It's the only way to balance it. Our other product is going to be calcium nitrate, and it's going to be aqueous. Our water is going to be a liquid. So we can take strong acid and strong base. We can make a salt and water. So let's look at this one. So we have two hydroxides, which means we need two H pluses. If we have two hydroxides, we're going to make two H2Os. It's going to be a liquid. And the other is salt. The other compound is going to be this cation, that anion, which is going to be barium chloride. Barium chloride has a formula of BaCl2, and this is going to be aqueous. We could write the net ionic, and the net ionic on this would be 2H plus 2OH minus goes into 2H2O as a liquid. If we took sulfuric acid and reacted with sodium hydroxide, again, we look at this and realize we have two OHs and two H pluses, so we're going to have two H2Os. Our secondary product is going to be strontium sulfate. Strontium sulfate is soluble, and so we're going to put an AQ here, and that is going to be our molecular equation. We could take and break these up and write a total ionic and a net ionic, but mostly you're going to be only asked to go to the net ionic on these guys, which would be 2H plus 2OH minus goes into 2 H2Os. If you want, you could do one instead because it's the same ratio.